Okay, now we are going to move into a little depth to the gauge problem. The essential point that I will address is the gauge covariance of the Schrodinger equation and how to really ensure the gauge covariance. But before that, let me discuss how do I get the classical Lorentz equation from the quantum mechanics. It may sound a little trivial, but it's not really. One has to be careful in getting that. So what am I going to do is the following. Let's start again with the, okay, the Heisenberg picture. I'll try to put a subtitle, Heisenberg picture treatment. Well, when you say Heisenberg picture, as we have seen previously, that there is a one-to-one correspondence with the Ehrenfest equations and Heisenberg picture equations of motion. Ehrenfest equation involves the expectation values. Heisenberg picture equations involve the operators in the Heisenberg picture, but they have the same form. Therefore, either way you can approach the problem having that one-to-one correspondence. So, but before that, we have to develop a recipe for the Hamiltonian. When you have free particle at free, then of course you know that its Hamiltonian is given as such. When there is no danger of confusion, I use the same symbol for the operator and the eigenvalues. Here, obviously, when I say Hamiltonian operator, I mean the momentum operator squared. So it is, there is no need to use the capital P because it's the operator that I'm talking about. In external electromagnetic field, it is known that this equation becomes, say, Q over C A squared plus Q phi. The external electromagnetic field or classical electromagnetic field is represented by the potentials phi and A. Okay. If it is classical, this Hamiltonian is classical. If it is quantum, this Hamiltonian is quantum. But the fields are still treated as classical. We need quantum electrodynamics for full quantum description of the particles and the fields together. Okay, that's beyond the level of this class. So I'm really making that qualifications that the field is treated classically. You have to be careful about that. There are several ways of doing this. The proper way, using correspondence principle, is start from the classical mechanics. Of course, for that you need Lagrange or Hamiltonian formulation, and construct first the Lagrangian and then the Hamiltonian, and then convert that classical Hamiltonian to quantum Hamiltonian. That's the usual pathway. Or Mr. Pauli has a recipe, so-called Pauli's substitution principle, at the equation of motion level. The other is at the Lagrangian or action level, and this recipe of Mr. Pauli is at the level of equation of motion level. Pauli is substitution principle. Notice that I don't really attribute too much value to this. This is a working principle, and there is a solid foundation at the action language. But it works so beautifully that if you are doing an equation of motion, instead of worrying about the action or anything, you just take the P mu and replace the P mu by the Q over C A mu. Well, notice that I have used the relativistic notation on purpose, but it's really because the zeroth component and the space component, because it's really the version of Pauli. But if I write it in components, because we are still in the realm of non-relativistic quantum mechanics, what Mr. Pauli means is that P is replaced by the P minus Q over C A, and the E, or the zeroth component, P0, which is E over C, is replaced by the E over C minus Q over C. Zeroth component of this is phi. So that is these two together are the information contained in this four-dimensional language. So let's sort of get used to it, because next semester when you are doing 508, you will be dealing with relativistic quantum mechanics, I hope, because that's what I was doing when I was teaching quantum relativistic 508 anyway. So that's de Pauli's substitution principle. And if you want, this is classical, all these things are C number, or it's quantum mechanical using the correspondence principle. These are operators. A itself is classical, but there is an AXT, and these are the operators, right? Classical functions of quantum operators. It's this sort of rather subtle, so pay attention to it. So if this is the case, you may say that in the space of functions of x, that is not in the abstract vector space, but in the coordinate language, that is when you expand this in terms of this position operator eigenvector basis, and you get these coordinates. That is the wave functions, as we have discussed last week, wave function, which satisfies the wave mechanics. And so for this discussion, perhaps it is, we could have stayed in this abstract language, or we could go to the wave mechanics language. Let's go to the wave mechanics language. And then in this space of functions, in this space, what are these substitution principles? It is P operator goes to P operator minus Q over C A of X operator if you want. This is classical, but the operator is here. And what about this? The C's obviously cancel. And E goes to E minus Q phi. That's important. What was E? Let me write it in the operator language. I h bar d by dt, right, goes to I h bar d by dt minus the Q phi. You may say, why didn't you write it that way? You're writing your criticism. Then we should write it as h bar over I del goes to h bar over I del minus Q. Sorry. For aesthetic reasons, if I'm writing it this one, this is equivalent to that, right? Explicit. The momentum is h bar over I the del in the space of functions of x. Otherwise, in the space of functions of p, it is just multiplied by p. In the space of functions of x, p is like that, so this is the substitution principle. I have, obviously, it is sort of something that you know quite well, but at the back of my mind, I have something quite subtle, so that's the reason why I am doing these substitutions in that sort of rather interesting exotic notation. Okay. So what is the equation? The simple free equation was I h bar d by dt plus h bar squared over 2m del squared on phi is equal to 0. I prefer to write it in this exotic way. So if I go to the electromagnetic interaction case, I replace it by I h bar d by dt minus q phi plus h bar squared over 2m del squared. Notice that if you take this expression, that's the replacement because that's momentum operator. What is the equivalence of this replacement for the del? Let me write it here underneath. You just chop off h bar over i's from both sides. That replacement is del goes to del minus I over h bar, so minus I q over h bar ca. So So I'm sort of motivating ourselves towards the introduction of so-called covariant derivative. From the Cartesian derivative, we have gone to something which I denote as the D, that's the covariant derivative. That's the substitution principle, right? Pauli is in terms of the P, or written as such, or P, or in terms of the operators in the space of functions of x. So if you want, you have a similar thing in here as well. Let me write this here, and then I will proceed. D minus IQ over H bar C squared. That's it. Psi equals 0. That is the new equation now, involving the electromagnetic interaction. So what I have done for the Cartesian derivative, or so-called del, and I can do the same for the IH bar dt. If I take this IH bar d by dt q phi and write it as IH bar factored d by dt minus or plus now I q over h bar phi. Well, as we are in non-relativistic quantum mechanics, I'm not paying too much to the contravariant notation. Instead of d by dx0, I'm using d by dt. If it was d by dx0, x0 is ct, then I would have an h bar c in here. So everything is consistent. There is no problem. So then the equation has the following sort of more aesthetic look. I prefer to write it in this fashion, and I will write the equation, and then I will switch back to Heisenberg picture treatment. But this is the Hamiltonian yet. I'm really playing with the Hamiltonian, and Hamiltonian is given as such. But here, this conversion of this equation at this level is sort of not to lose track of it. I am doing it, although I'll go back to discussion there in a moment. So what is this? IH bar d by dt, IH bar, I will denote this as the dt, as a definition. Covariant in time. So IH bar dt plus h bar squared 2m d squared psi is equal to 0. So that's rather nice, because I'm employing the covariant derivatives, so it will enable me to check the covariance of this equation quite easily. Once we have these, let me encircle them in color. Once we have these new covariant derivatives, and this one. These are the notations. Isn't that nice? In this new notation, it looks so much similar to this one, right? It is this free equation, ordinary time derivative, ordinary space derivative in 3 dimensions squared. It is the covariant time derivative and covariant space derivative squared. So as long as you remember the geometric meaning of the covariant derivatives, that is the ordinary derivative minus a part which is really connection in space and time. But that's a little too much, perhaps. You don't have to remember this geometric meaning of the electromagnetic field forming the connection in space. This is good because this will enable me, it's more suitable for proving the covariance. Very suitable form for demonstrating covariance of the equation. So let's give a short detour now. Let's keep it there to be picked up in a moment for this actual covariance demonstration that's very much needed, because all the rest, electric dipole approximation, Landau level problem, Aronow-Bohm effect, Aronow-Kasher effect, magnetic monopoles, all that beautiful and rich family of physical problems would be treated by that equation in that form because of the gauge covariance. But as I promised, although deviated a little bit. Let's see whether Heisenberg, in the Heisenberg picture, which is similar in spirit to the Ehrenfest theorem, which is the classical version. Let's go ahead and let's work out that equation. Go to the Heisenberg picture equation or use the Ehrenfest equations to see whether we can reproduce Lorentz force equation of the classical physics, right? Heisenberg picture treatment, that's what I'm talking about. Now we pay attention again to the following distinction. Notice that in this Hamiltonian, we have this combination appeared, not the, well, as compared to p squared over 2m. Let's compare this against that expression. So notice that it's not the p, but it is the p minus q over ca. So this quantity is what is really corresponding to the kinetic momentum, right? So mv is p is equal to p minus q over ca. We will give this a name. We will call it pi as a shorthand. So when you write it as pi squared over 2m, it's very similar to the p squared over 2m in language, but they are different things, obviously. Now, there is so much that one can talk about in this context. The Lorentz force equation is, as it involves E and B directly, it is gauge invariant. So what are the gauge invariant quantities in classical physics? The left-hand side is mv, so it must be mv. Obviously, p is not, numerical values are not gauge invariant. The numerical values of p depends, I'm using a careful language. I cannot say p is gauge invariant or not. It's something which is not really directly related to the gauge as an operator or as a dynamical variable. Its numerical values may differ from one gauge to the other on a trajectory. So that's the careful language you have to use really when you are talking about it. But it's only natural that P cannot be gauge invariant if this is gauge invariant, because we carry over this information from classical mechanics that this must be, as it is in the left-hand side, as the equation is gauge invariant, so this must be gauge invariant. As this changes under gauge transformation, goes to A minus del F, obviously this should not be gauge invariant and change accordingly to compensate this additional piece. You see why canonical momentum, which is the generator of the translations, is not a gauge invariant quantity. But MB, kinetic momentum, is. Strangely enough, that is the case. So let's run through a quick derivation of the Heisenberg equation. What is the Heisenberg equation for general operator? dO dt, in principle, if it depends on time, for the observables x or p or whatever, obviously that's not valid. But for, it may depend on explicitly, so I over h bar, h and O. So when you have dx dt, choose O, this generic operator O, as x, and let's look at this dx dt. As the x doesn't depend on time explicitly, that first term is not there, and the second is I over h bar, Hamiltonian, and the x. Yet I'm using the arrow, but at some point I have to resort to the index notation, because when you are having h is quite non-trivial, therefore you need to resort to that. So what is the Hamiltonian in this new notation? It is 1 over 2m pi squared plus q phi, which is a function of x. Being a function of x, it commutes with any function of x, so this term doesn't contribute. It is the first term which contributes, I over h bar, 1 over 2m pi squared nx. What is that commutator? That commutator can be computed without too much difficulty. It's not a trivial commutator, but what do you do? It's pi squared with any component xi. So let me compute this in here next to this. Pi squared with xi is pi j and pi j, go to the index notation, and it's pi j and pi j, first factor to the left and second factor to the right, and it has two terms in it. Pi j xi, and pi j xi pi j. So that's the usual decomposition. There's not too much a problem. And pi contains p, the canonical momentum, and a function of a, so the second term doesn't contribute to those commutators. X, any component of x commutes with any function of x. So this one is just pjxi. So what is it? Minus IH bar delta ij. Similarly, minus IH bar delta ij. You have twice of them. Therefore, minus 2IH bar pi I. So pi squared xi commutator is minus 2IH bar pi I. If we substitute this in here, so what do we get? 2 cancels the 2. H bar over I cancels this. So it is 1 over m pi I. Compare these two equations. Now let me put back the index to the arrow so that we are consistent. dx dt is 1 over m times pi. So that is really verifying my identification of the velocity with the pi, right? Because this is dx dt is the velocity operator, time derivative of the position operator is the velocity operator, is 1 over m pi. Pi is 1 over m p minus q over ca. So it is this thing really, the kinetic momentum, which appears in here. Not the canonical momentum, but the kinetic momentum squared. That's nice. So the second leg is, for this equation, we have first chosen O as x. Now I will choose O as pi. Well, not p, but pi. Why? Because pi is the kinetic momentum and it's the gauge invariant quantity, the lesson we learned from classical physics. If I use p, which is not a gauge invariant quantity, then you'll not get a gauge invariant expression, obviously. So the choice should be made cleverly. So the second choice for the O, for this generic equation, involving generic operator O, I will choose the pi, which is the mv, right? So the second is d by dt pi. Do we have a contribution coming from this term? This time, yes, because in pi there is a. So it is minus d by dt minus q over ca, right? This term will have a contribution from the partial derivative thing, minus I over h bar, h, let me write it, it's fully 1 over 2m pi squared plus q phi, and the pi, right? Because I'm computing this. Well, this term is to be retained. It's going to be useful. And there are two terms in here. So what is it? 1 over 2m I over h bar pi squared and pi is one term. Second term is I over h bar, iq over h bar, phi and pi. Now I will resort to the index notation, obviously, because if I cannot pursue any further with those vectors. So let me think of it as pi I, and let me think of it as a pi I. Eventually, I will restore it, put the arrow back. What is this? P minus a function of x on here, minus, so it is q over c, minus pi phi. Pi on phi is h bar over I, or minus, there is another minus, plus I h bar di phi. Nice. So you see, from here, I get a contribution like this, I h bar, right? Sign, let's check the signs. Pi I is h bar over I, or minus I h bar. There's a minus plus I h bar, the gradient of phi. And so together with this one, i's gives you minus h bar cancel. So it is, this entire thing is minus q. That minus sign is nice, right? Because we know that electric field is minus the gradient of phi minus 1 over c dA dt. It's in here. So these two terms nicely combined. Let me write them. So there's a q minus del phi minus 1 over c dA dt. You see, when you do things, it's so beautiful of physics. You recover the classical physics or the Heisenberg equation version of the classical Lorentz equation. That's the first term. This together with the second, but there are still those terms. Let me write them down. So what is it? Minus 1 over 2m I over h bar. Let me go back to the index and I will put the arrow back. Because to complete this, I need the index notation successfully completing it. Pi I. So what do we get from here? Pi squared and pi I commutation. It was p squared and p, it would be 0. The canonical momentum, which is the generator of the translations, commute among each other, right? Pi pj is 0. But pi I, pi j is not 0. What is pi I, pi j? Let's compute that. It is really a non-commutative. This is the first primitive appearance of non-commutativity in physics for these kinetic momenta. What is this? First of all, let me compute this primitive, and then I will use it to compute this pi squared pi I. What is this? It is p minus something, p minus something, p and p commutes, a and a commute. So first to first, second to second terms commute, and it's only the cross terms which give you any contribution, right? Minus q over c, ai, pj is the first term, first cross. The second cross is pi minus q over c, pi, aj. Or q over c, pj ai minus pi aj, right? That is reversing the sign using anti-symmetric property of the commutator. I have this thing. So what is this? Minus ih bar del j ai. And this one is minus ih bar di aj. So altogether what? Altogether I have I h bar q over c, I h bar q over c, indeed so, di aj minus dj ai. Okay. What is this? This expression? I claim that it is epsilon I j k b k. Let's demonstrate. To save some time, I go from the backward. So what is bk? Bk is epsilon klm dl am, right? Contract the case. So epsilon il epsilon jm minus epsilon im epsilon jl. Sorry, deltas, of course. You are contracting two epsilons, you get deltas. So il and jm, so this expression becomes di aj minus dj ai. Indeed, that expression I have demonstrated. So epsilon ijk bk is this. So it is a really beautiful geometric expression, right? So what do I have? I h bar, I h bar q over c epsilon I j k b k is this expression, pi I pi j. As compared to pi pj, which is 0, this kinetic momenta pi I pi j is very nicely geometrical, I h bar q over c epsilon I j k b k. So let me use that in completing that commutation relation. That is, this one is the only one missing, right? I need pi squared pi I. So what is the, using this, what is pi squared pi I is pi j pi I plus pi j pi I pi j, the usual distribution. These are computed. But pay attention to the ordering of the index. Ji order. I have finished that computation ij order, so let's change the ji order in here. I is first, j is next. First, next. J is first, I is next. So I will convert this into I over I h bar q over c epsilon j I k b k. This one and this one are both that expression. So what do I have altogether now? I h bar q over c epsilon j I k pi j b k plus b k pi j. You say, what? Is this what I really wanted to? So let me substitute in the here. That's where I have to put that in, and then we'll see. D by dt, pi I. Let me put in the indices now, not to get confused. That's the left hand, the pi I. Q minus di phi minus 1 over c di dt plus 1 over 2m I over h bar times this thing. I h bar q over c epsilon jik. Now let me go to ijk. Change the sign to go in the correct logic, because I is the free index, so I need to change the sign. If I go to, let me write it, epsilon minus ijk pi j bk plus bk pi j. Now let me do some cancellations before proceeding any further. H bar cancels H bar. I and I is minus. There is another minus sign plus. Here. Yes. I and a minus, there is another minus sign plus, so there is a Q over C. There is M, 1 over M. Epsilon, these things are cancelled. Epsilon ijk pi j bk plus bk pi j, right? I will use eraser, please. You, if you want, you use a different line. Let's put the m's in here. What is this? Pi over m's are v's, right? Because we have shown that pi's are the mv's. This mv, epsilon ijk is pi j bk. It is like pi or v cross b. There is a 1 over 2. Let me not forget the 1 over 2. That's a tremendous mistake. It is really epsilon ijk v cross b. But because of the operator ordering, I have written them in the first in the left and in the right? And Q over C is, what was the Lorentz force equation? Q over C, the second term, Q E plus Q over C, V cross B. Do I have the V cross B? Yes, and in a symmetrized manner. Operator ordering is important. When you are in quantum mechanics, you have to operator order. That's 1/2 and times pi b in this order, b pi in the other order, 1/2. It is the symmetrization of the operator. We indeed reproduce the Lorentz force equation in here. The first term was already here, and that's the second term. There is an overall Q over C. Nice. So we have reproduced, using Heisenberg a picture equation of motion, we have reproduced the Lorentz force equation. This is quantum mechanical, so operator ordering is taken care of. If we go to the Ehrenfest theorem, take expectation values, then there is no problem. You indeed get Q times E plus Q over C, V cross B. Next step is to consider now the gauge covariance of the Schrodinger equation. This was a discussion in the Heisenberg picture. Now I go to the Schrodinger picture, and I go even further, go to the wave mechanics. That is the equation in terms of the coordinates in the position eigenvector basis. Okay. So the next subject is covariance of the Schrodinger equation. Now you'll see the reason why I have written that equation in that beautiful form. What was the equation? IH bar dt plus h bar squared over 2m d squared phi xt is equal to 0, where dt is d by dt plus I q over h bar phi, and the d is d minus I q over h bar c a. This sign difference in the covariant derivatives in time and space is a reflection of the fact that if you were doing relativity, probably whenever you are doing electromagnetism, you have to use relativity, really, even in the context of non-relativistic quantum mechanics, because light or electromagnetic field part is intrinsically relativistic anyway. So it really carries information from the theory of relativity, even in the non-relativistic quantum mechanics. That's the reason of this difference in the covariant derivative. The metric is 1, minus 1, minus 1, and minus 1. And space momentum is P vector is h bar over I, the gradient. Time is IH bar d by dt, or minus h bar over I d by dt. There's such a beautiful difference. That difference is a reflection of the Einstein theory of relativity, and you'll see more of it when you move into the second part of the quantum theory. But don't think that I'm doing a typographical error in here. This is really what it should be. It's correct. This has an advantage in demonstrating the covariance. If this is the form of the Schrodinger equation for a charged particle in the presence of external electromagnetic field, with those beautiful definitions of covariant derivatives, so what if I go to a new one involving now another primed family of electromagnetic fields. This is unprimed, phi and a. And suppose I go to now IH bar dt prime plus h bar squared over 2 d prime squared. Actually, I should do it slightly differently. Naively, this is correct, but I need to be careful. What do I mean is IH bar dt psi prime. You'll see the reason why this is really, at least aesthetically, more superior to the original one. Well, in the other gauge, the so-called primed, when I am using the primed fields, it must have this form. When, what is the meaning of dt psi prime? Dt prime and psi prime. And dt prime involves the phi prime in here, d space prime involves a prime in here, okay. But notice that I have also changed the psi. I didn't leave it untouched. What is where do I get this lesson from? Remember in the original, that simple exercise, some of you missed that introductory part, when we were discussing the 0 point of the potential energy, we have realized that although in classical physics, equations of motions are insensitive to the choice of 0 of the potential energy, in quantum physics, it is sensitive because the wave function itself, or state vector, should be multiplied by a compensating phase factor. So I say, based on that the initial information, I say let's also transform the size. But obviously these transformations must be unitary transformations because we want to preserve the norm. In these two different looking equations, actually they're equivalent equations. One is chosen in the gauge phi a, and in the other one is written in the phi prime and a prime gauge. But we can afford to change the wave function, but wave functions can undergo only a unitary transformation to preserve their norms. Norm preservation is only guaranteed by unitary transformations. Okay. So what I am doing is that when you are having this a prime is equal to a minus d f, and phi prime is phi plus 1 over c df dt, then I say psi prime should be taking the old psi in the unprimed gauge and multiplying it with a unitary transformation u. Do I know the form of u? No. In a sense, this scheme is so tight, I will construct the form of the u in order to have this covariance. That is, whatever that expression is, it must have the same form, provided that I change all of them simultaneously. A goes to a prime, which is this. Phi goes to phi prime, which is this. Psi goes to psi prime, which is this. What is the form of u? I will determine it along the way. So while achieving the covariance, I will be able to find the u that psi should undergo. How do we do this? If you look at the form of this equation, I have an expression of this form, for instance. What is it? It is d by dt plus I q over h bar phi prime times u psi, right? This is really what that is. I have substituted the prime quantities, what they are equal to. Actually, I should have written it here explicitly without you losing too much time. Okay, let me do it cleanly. Phi plus 1 over c df dt That's really it. Right? So this first term acts on both of them. So what do I have? d by dt on u psi plus I q over h bar phi u psi plus I q over h bar c df dt u psi. Wow, it becomes so complicated, really. Sometimes when you get into these computations, at some point you may fall into desperation, but don't worry, it will unfold easily. Instead of specifying the recipe at first, I wanted to reserve it to a later stage, so I'm moving in that direction now. I'm still at the time derivative part. Even in the first term, this one has two terms, right? du dt psi plus u d psi dt. So when you really unfold this, there are two terms in here, two terms in here, four terms. It looks too crowded, but we do the following trick. Notice that this second term and the second term in both groups, if I put them together, so what do I have? So I'm still writing this. dt psi prime is u d psi dt plus, I'm grouping these greens, I q over h bar psi. Really. That's right. U factored, there is a q over c, sorry, phi and psi. Let me leave this psi out. So this is much better now. This with this. What is this? This is really dt psi. So the first term, from the second and second in both lines, I managed to get a u times the dt psi originally. What about the other terms? Other terms are the following, plus there are a group of extra, du dt plus I q over h bar c u df dt psi. It is this one and that one, this one and the other one, this one. So the covariant derivative in time transforms as u times the covariant derivative. If this thing vanishes, if I set it equal to 0, why do I have that freedom? Yes, because I haven't specified the form of the u yet. I have left it as yet arbitrary unitary. So this equation will enable me to determine the u. It was the arbitrary unitary, yet if I now set that equal to 0, I can determine it. How? To determine it, I parameterize u as e to the ig of xt. G is another unknown, u is unknown. Unitarity is guaranteed. If this is real, there's a minus, there is an I in the front, so this is unitary. So what is this equation now with that parameterization? I dg dt times u itself again, because it is the derivative of this times itself, plus I q over h bar c u df dt is equal to 0. Factor the u's, and what is left over? What is left over is i's also go away, dg dt df dt. So d by dt g plus q over h bar c f is equal to 0. Isn't that nice? I have been able to determine the g, which is parameterizing the u, in terms of the f which was originally there in the gauge transformation. So these transformations are intermingled. Whatever gauge transformation you are using to redefine electromagnetic fields external, you are using that same F in a rather interesting manner to redefine to compensate your wave function, as in the case of 0 point energy of the 0 point of the potential energy, as we have opened up today's lecture, right? So what do I get? Up to a constant, constants are very important because they are just pure phases. Up to a constant, G is, if I solve this, G is minus Q over H bar C F. So that G is not just any G, but it's using that F. So what is the psi prime? U is then? U is e to the I G, which is e to the minus I Q over H bar C F of x t. So the picture is complete now. If you subject the electromagnetic fields, which are external entities, transform like this, A like this, and phi like this, then psi, the wave function, also should transform. When all these are transformed like this simultaneously, you get the covariance. This equation and that equation has the same form. So Schrodinger equation is gauge covariant. You are free to choose any gauge, it means. You are free to choose any gauge. Physics will not be affected. Isn't that nice? So there are so many things that this important observation buys. Let me copy that result in here, because it was arbitrary unitary, now it's determined. You use a new line, please. I will add in here e to the minus I Q over H bar C F of x t times psi. Under the simultaneous transformation of all the fields and the wave function, you have a covariant equation. What kind of things that this buys for us? You can really trade off the gauge fields, particularly pure gauge fields, which yield no electromagnetic field directly. You can rotate away or remove the potentials from the Hamiltonian and transform those potentials put it in the phase of the wave function. Or if you have a gauge dependence of the phase of the wave function, you can transform it back to the Hamiltonian. I will demonstrate this perhaps, but we should give a very short 5 minutes break here, because today I have to stop the lecture at 1/4 instead of 12:30. So just get a breather and stretch your legs and come back. We'll continue after 5 minutes. Okay, I'm not going back to the office. I'll stay in here, wait for you.